Welcome back. So we were discussing about the possibility of finding out which particular modes of a given modes of vibration for a given molecule will be infrared active or Raman active, and if one is infrared active, then in which polarization, which direction it will be, the transition will be taking place. So we need to know about the selection rules, right? So basically we want to find out which one of them is infrared active and which one is Raman active, or which one are Raman active. So let's start with formulating how we can find out about the possibility of one particular type of activity, that is infrared active or Raman active. So what are the selection rule associated with that? So now we will talk about the selection rule. Selection rules of molecular vibration. So we know that any normal mode which is expressed as it can be expressed as the wave function, as a wave function, and we can write this wave function as as a function of the normal coordinate. So normal coordinate is the coordinate about which the the vibration takes place. So this molecular vibration, the wave function for this normal modes, I can write as psi n, which I can write as Ni okay. And okay. So you can find this in any textbook of quantum mechanics. So here in this expression, what we have a normalization constant. So Ni's are normalization constant, and this xi I is the ith normal coordinate. Okay. Fine. And this alpha, it's a function of the frequency of the normal mode. So alpha I can write as by this. Okay. So now this is a wave function for any particular normal mode. So therefore, as we have discussed earlier, this wave function should form the basis for an irreducible representation of the particular point group to which the molecule belongs to. All right. So here one thing I forgot to mention, this is a polynomial. This is called Hermite polynomial. which is a function of this coordinate. So here I have root over alpha I xi I. Now this one is such that for n equals to 0, n equals to 1, 2 and 3, the values are different. So this n here represents the vibrational quantum number, right. So if it is in n equals to 0, that means we are in the ground vibrational level. And one more thing, like I express this normal mode in terms of this equation. This is valid for a particular model, which is the harmonic oscillator model. So most of you are probably aware of this. So now this Hermite polynomial, if I have n equals to 0, then I have a value of 1. So if I consider H1 in general, I have a value of 2x. Okay. So then H2, so similarly I can write for H2 and H3 and so on. So this gives me a value of 4x square minus 2, while this gives me 8x cube minus 12 and so on. Okay. So now when I operate any symmetry operation on these wave functions, what should I get? I should get either plus 1 or minus 1 and multiplied by the same function back, right. That's what it should be, because these wave functions form the basis for the irreducible representation of this particular molecule that we are considering. And if we are considering a one-dimensional irreducible representation, then obviously I should have this plus or minus 1 as character. Now if I consider n equals to 0, okay, and if I have many normal modes having many many number of normal coordinates, then all of them, if they are at the lowest most energy state, that is the lowest vibrational quantum number 0, then I have my molecule in the ground vibrational level. So I need to know what is the symmetry property of this ground vibrational level. Now this ground vibrational level, what is the form of the wave function at the ground state? So at ground vibrational level I have H0, which is giving 1. So therefore what I have is psi 0, okay, for any ith normal mode as ni e to the power minus alpha I by 2 and xi square, because the other part is 1. Now at this condition, what is the symmetry of this particular function? Or in other words, if I ask that which IR of the point group this particular function which is at ground state will transform as. So let us find out. So here if I operate R on psi, I will get something out of this, right. So here for psi 0 I have a function where suppose this is a function of this coordinate. So the symmetry of this function is governed by this normal coordinate, right. Now how do I get this normal coordinate? I get this normal coordinate by the symmetry adapted linear combination of this atomic motions. Okay, so if this xi transforms as one particular irreducible representation, then that will be the irreducible representation that my this function will also transform as. So if I apply an r on this xi, so this is a coordinate system, so r will either change it to +1 or -1. Okay, so this will give me plus or minus xi I. So in whatever case, either it is plus or minus, if I apply r on this function, this is going to give me back always +1, right, as my +1 times this function. So therefore, if I operate all the symmetry operation, okay, so if I perform all the symmetry operation, the characters irrespective of the operation is always going to be +1. What does that mean? That means this is this particular function, which is the ground vibrational state wave function. It will form the basis of totally symmetric irreducible representation. So at ground state, the normal modes at ground state, normal modes will form the basis for totally symmetric irreducible representation. Now here obviously I assumed something. I assumed that this energy levels that I am talking about is non-degenerate. Okay, that is only one particular energy state is there, one particular state is there for that particular energy value. Now if I have a situation, if I would have a situation where I have more than one state having the same energy, so I have a case of degenerate state. So there also I can very easily show that this particular property of the normal modes at the ground vibrational level remains intact. So how can I do that? Suppose I have here I consider that one particular normal coordinate. So suppose I have say xi A and xi B, they form my set of two degenerate normal coordinates for two normal modes of vibration at the ground state. Then I can express this the transformation of xi A such that xi A will form something like say xi A prime, and if these two are degenerate as I assumed, then what will happen? I can write this one as something like say R A times xi A plus R B times xi B. Now if my xi A is normalized, then this coefficients R A and R B also will be taken in such a way that this guy is normalized. So if I take this psi A square is equal to 1 in a normalized condition, then that will imply that psi A prime is also equal to 1. So both of them are normalized. Therefore I have no problem because I can express psi B also in the same way. So therefore the matter again becomes like the same case as we discussed earlier. So therefore irrespective of the fact whether this normal mode of vibration we are considering when it is in ground state, is it degenerate or non-degenerate, it will always form the basis for the totally symmetric irreducible representation of the particular point group that we are considering. So, this is true always. Now, what will be the case of excited state, right? So, we have talked about the ground state, that is, if I call psi 0. Now, I am talking about excited state. So, the symmetry of the excited state will be governed by this part, right? Why? Because we have just seen that this part, no matter what, always will be transforming as the totally symmetric irreducible representation. So, I am not bothered about this part anymore. So, I have to take into care of this particular symmetry. So, as we said earlier, the first excited state, or the n equals to 1, h is h1 is equals to 2x when I am talking about h of x, correct. So, if I am talking about psi 1, I will have its symmetry governed by this. So, here I have say x, okay. So, if I write in terms of this normal coordinate, I can replace it here. So, I will have some sort of symmetry, fine. So, here it will be an odd symmetry. Now, similarly I can find out about psi 2. So, psi 2 again it will have contribution coming from h2, which is, so this is again an even function. So, the nature of the wave function at the excited state will be governed by the symmetry of this normal coordinate, correct. So, either I will find an odd function or an even function. Now, in case of vibrational transitions, so what are the different kind of transition from which state to which state we can write. So, suppose I have a molecule which has total overall k number of normal modes, okay. So, let us consider a molecule with a number of normal modes equals to say k, associated with k different normal coordinates. So, I can write down the total wave function, okay, of this by taking a product of each and individual wave functions. So, now suppose I have say psi 1 at particular energy state, and let me call it as a 0. Then make a product with next one, sorry, psi 3, so on up to psi k. Now, this 0 within the parenthesis, it gives me the particular quantum number, okay, where this particular wave function is residing, that is a particular normal mode is residing. So, here in this particular case I am considering that all my normal modes, the first, second, third or the kth one, all of them are residing in their 0th level, that means all of them are in ground state. So, therefore, this total wave function of this molecule is in ground state. Now, suppose one of these, suppose the jth one, okay, is residing on the n equals to 1, that is the first excited state. Then how can I write? So, this one overall I can in general write as the psi as okay, and I can write this one as n, okay. Now, suppose I have a situation where my psi is, say, psi j is residing on state 1 and rest of them, that is I minus 1, is still residing on 0th vibrational level. So, this configuration is the first excited state configuration, and this means that one of the normal mode must have, like what was the situation here, from here one of this jth normal mode has made a transition from state n equals to 0 to n equals to 1, and this type of transition is known as fundamental transition, fundamental vibrational transition. There are other type of transitions. Suppose I would have this particular jth normal mode would have made a transition to state 2. Suppose it would be psi of j2, then that would mean that it has undergone 2 successive transition from 0 to 1 or 0 to 2. That would give you the first overtone. If it would have gone to third level, it will give me second overtone. Also, it could be that instead of only one normal mode, it could be 2 normal modes. Say for example, if I would write psi j and psi L have gone to state 1 and the rest of the wave functions, that is normal modes, they are residing at level 0 still, then this would be called a combination transition. So, we can have this combination transitions, we can have this overtone transitions, all these things apart from this fundamental. Now, the matter of fact is the fundamental transition probabilities are way much higher than the overtone, or on the other sense we can say this overtone transition and combination transitions, they are much less probable compared to the fundamental. So, we will stick to the fundamental transition only. Alright. So, if I write down the excited state wave function for a particular fundamental transition as by a different symbol, say I write down as say I will write that this is psi v, say I as my ground state wave function, where all of the normal modes are residing on the 0th level, while say psi v j is the case where one of the normal modes is residing in the first vibrational level. Okay, I mean v equals to 1, right. So, that a transition from here to here will give me the fundamental transition, right. So, I am writing in this particular notation now. Now, we have to find out that how do I know about the transition probabilities. So, if I want to consider this fundamental transition, I can write the transition moment integral as psi v j over all space. This is my transition probability. Now, in this transition moment integral that I have, this mu is a dipole operator, so which can be broken in terms of the charge and the distances, and this r associated with this can be explicitly written in terms of x, y and z. So, this we discussed some time back very briefly. So, this one I can rewrite in 3 separate integrals. So, in terms of x, y and z, charge has nothing to do with this integral, so we do not consider about that. And I can have the same thing, say instead of x, in another case I will have y, in another case I will have z. So I will have total 3 integrals which are possible. Now I need to talk about the the result of this integration. So this particular transition moment integral will survive only when the direct product of this. So what is that? Because each of this functions, be this function or this wave function, will transform as the one of the IRs, or it will form the basis for one of the IRs of the particular point group that we are concerned. So if I replace these wave functions by their symmetry property, meaning irreducible representation to which they form the basis for, then the direct product of those irreducible representation either should be equal to the totally symmetric irreducible representation or should contain the totally symmetric irreducible representation. Fine. So then only I will have non-zero value for this integral, otherwise this integral will vanish. So that is true for each one of them, okay, either x or y or z integral. Now I have just seen that this psi I, which I took as my ground state, fine. So in case of psi I, it forms the basis for the totally symmetric irreducible representation. So fine, that is true for any ground state vibrational level. Now we are left with this two, because I do not have to worry about this one. Whatever will be the symmetry of this will be the symmetry of this integral, right, because this belongs to totally symmetric irreducible representation. So now what that does mean, that this particular wave function, that is the wave function of the excited state, must have the or must belong to the IR to which x belongs to, correct, because only when the irreducible representation corresponding to this wave function and this function are same, the direct product is going to contain the totally symmetric IR, correct, and this direct product must yield totally symmetric irreducible representation, or the product of this must contain the totally symmetric irreducible representation in order to have a direct product with this one, which is already totally symmetric in nature, will give the non-vanishing value for the integral. So in other word, if I say, what do I have it here? It says, and this we are talking about the infrared transition, right. So the transition, infrared transition, is possible only when the excited state contains the irreducible representation corresponding to the excited state wave function must be the irreducible representation to which either x or y or z belongs to. Then only I can have the transition. So that is my selection rule, right. So this one I need not worry about. So I only need to look at the excited state wave function and its corresponding irreducible representation, and then find the irreducible representation to which x transform as. If these two are not the same, their direct product is not going to give me the totally symmetric irreducible representation. So I will find out which of this or which of these integrals will survive, and I will get the infrared activity. So this is about the infrared activity. Now what about the Raman activity? So in case of infrared spectroscopy, I deal with this integral, okay, where the operator is nothing but the xyz Cartesian coordinate. What happens in case of Raman? I have a similar type of transition moment integral involving psi of where this P is nothing but the polarizability. So, I will have many transition moment integral possible based on that what component of the polarizability tensor we are talking about. So, the polarizability tensor has component like say xy, xz, yz, okay, or x square, y square, z square, or their combinations, for example like x square minus y square, x square plus y square, and all those things. So, this individual functions, they form the component for this polarizability tensor. So, I can have the transition moment integral for Raman transition, Raman vibrational transition by taking this functions x, y, x, z, and so on. Now, rest of the things will follow as such. So, I need to find out. So, instead of this particular one, I can have an integral which looks like say xy. So, the case becomes same again. This I am not worried about because this already belongs to totally symmetric irreducible representation. Now, this normal mode, which is the excited state wave function, and this particular function xy, they must form the basis of the same irreducible representation, and then only this transition moment integral will survive. So, thereby all I have to do, I have to look at the character table and particularly the area 4 of the character table where you find this particular functions, okay, and that will tell you exactly that okay, this xy, this function, it forms the basis of this particular irreducible representation, or xz forms that particular irreducible representation. So, you exactly know what is the irreducible representation according to which this wave function will transform. Okay. So, once you know that, you look for that irreducible representation to which the operator, that is xy or xz, will transform, and then if they are not same, you got your answer. It is not, this direct product is not going to contain the totally symmetric IR, therefore this this particular integral will vanish. If it contains the totally symmetric IR, the integral will survive. So, there will be a definite probability of transition. And one thing here, like for this kind of transition, you will be able to say that if this x integral survives, then not only the transition is allowed, because if I am talking about the allowedness of infrared transition, then I will see either one of them, that is x integral or y integral or z integral, survives, or more than one survives. It can happen that it survives in each case, or it can happen that it survives only in one case, that is in case of x or y. So, if it survives in one particular integral, then I call this transition is allowed and allowed in that particular direction. Say for example, this is allowed along x direction, then I say this transition is allowed and this is polarized in x direction, or it is x polarized. Similarly, if I have both x and y having both x and y integrals having non-zero value, then I will say the transition is allowed and the transition is polarized in xy plane. Okay. In the same way, I can talk about for Raman transitions also. So, after knowing this, I am ready to now go back and talk about the like we found out certain set of irreducible representation which represents the normal mode, genuine normal vibrational modes for N2F2 molecule, right, in the previous class. So, out of those normal modes which are Raman active, which are infrared active, that we can now state. clearly. So we will do that in the following class, and till then, have a good day. Thank you very much.